Welcome back to our little mini unit on topic 3, implicit differentiation, derivatives of inverses, and related rates. We've already covered all we need to for implicit, though we'll continue to use it every day, including today. We're actually doing the second of 2 lessons on inverses today, and then we still have related rates to get to later on. So let's finish off inverses. And last class, of course, we covered derivatives of trigonometric inverses. Those are a pretty specific brand of inverses. Today we're going to expand to unknown inverses, or we could maybe think of it more generally as the derivative of the inverse of any function. So instead of having to memorize just specific derivative trig formulas, which you do need to know, this one is going to give us a single formula for the derivative of any function's inverse. And the nice part is this is actually the last formula you really have to memorize all year long. There are other things that you'll need to remember, but in terms of straight formulas, this is the last one. Let's get to it. You have an opener on here. Of course, it's going to have to do with inverses. So please go ahead and see what you can do with A through D, and then we will share out results at the end. All right, so hopefully you've unpaused and you're doing okay here. Here are a couple things that we should know. If you do f of g of x and the answer is plain old x or g of f of x, then what do we know about the two functions? Well, we know that f and g of x, so f of x and g of x, are inverses. In fact, that's the definition of the inverse. Hopefully we understand why that's true as well, because ultimately what you're doing is you're taking a function that has things happening to x, and you're substituting into a function whose sole purpose is to undo everything that happened to x and g of x. For example, if g of x was something like x is multiplied by 2 and then added by 5, if we plugged it into its inverse would subtract off the 5 and divide by 2. It undoes everything happening to x. And once you've undone all the operations, you should just be left with plain old x. Now, what are some properties about inverses you might remember? Well, this could be all over the place. So hopefully you came up with maybe 3 or 4 of these. But it's okay if you didn't come up with too many. Just a quick rundown. You can always look this up later. For inverses, you always swap the domain and range. So if we have a domain on the original function that's something like 0 to infinity, and we have a range that's like negative infinity to positive infinity, then on the inverse, these would swap. So on the inverse, the domain would go from negative infinity to infinity, and the range would go from 0 to infinity. And that's always the case, with the one weird exception of our inverse trig derivatives, where they had to restrict the range because otherwise it wouldn't end up being a function. What else? Well, in tables, and this is actually fairly important, if you have one function, x comma f of x, and you had something like 2 comma 3 and 4 comma 5, and then you wanted to look at a table of the inverse, x comma inverse of x, that stupid -1 notation, well, it's going to be the exact same table except you switch the x's and y's. What about their graphs? Well, in terms of their graphs, we always, if we have some sort of function that looks, I don't know, like this, then if you picture the graph or the line y equals x, then that an inverse always has symmetry across the line y equals x. So we can, have that, and we're just going to flip it over, and it's going to look exactly the same, right? Just flipped over. Okay, something like this. And I think maybe you could picture it from there. Yeah, all it's going to do is just flip over and look exactly the same. And I'm actually struggling with what it's going to look like. Little like this, give or take. There's our nice little symmetry here. So there is something else, and I think that's really all you need to know about inverses. A little bonus fact is, how do we know if a function has an inverse, which is also a function, without doing any math? Well, it might be easiest to see with a quick example. If you took a parabola, right, y equals x squared, will its inverse be a function? Well, one other fun fact about inverses is when we reflect across y equals x, a lot of times you might hear that it's rotated 90 degrees, and that is fairly accurate. right? Looks something like this. So we should notice, of course, that my original function, x squared, is not is a function. It passes the vertical line test. However, its inverse is not a function. Its inverse is just classified as a relation or a relationship. Well, how would we have known that initially? Well, it all is about these lines, these vertical lines, or in this case, the horizontal lines. So if you're ever interested, you can always perform the horizontal line test. And so if I do the horizontal line test on my parabola, notice it fails the horizontal line test, because just like the vertical line test for a horizontal line, if it passes through a graph more than once on a horizontal plane, then its inverse will not be a function. How come? Well, it has to do with inverses. If this is a horizontal line here, then on the inverses graph, this will become a horizontal line. So if it touches twice here, those exact same 2 points are here because you switch the x's and the y's, right? If this is the point 2 comma 4 and this is the point negative 2 comma 4, look at what they have in common. They each have a 4. And when you switch them, now my new points on my inverse are of course going to be 4 comma negative 2 and 4 comma positive 2. They have the same x value with 2 different y's. We are no longer a function. And last but not least, because this is easily confused because I mentioned it before, it's silly notation. This right here means the inverse. Most calculators do not have an inverse button. Putting something to the negative first power does not create the inverse, unless you have an inverse button or we're discussing matrices, but that's something completely different. Versus this guy, which is, of course, the power of negative 1. So f of x to the negative first actually means 1 divided by f of x to the positive first. But that is not what this means, and that we're going to be using the inverse notation for the most of today. All right, let's take a look. There are 8 questions here. Your goal is to evaluate the following without a calculator, please. So there are a whole bunch of different notations here. I wish you the best, and unpause whenever you're ready. All right. Hopefully you got through all of these. Let's make sure we're comfortable with this. We do f of x to the negative first. Well, that just becomes 3x minus 7 to the negative first. And we want to make sure that you know that means 1 divided by 3x minus 7, right? Technically to the positive first. It, however, does not mean 1 over 3x minus 1 over 7. We can't distribute a negative 1. That kills puppies when there's addition or subtraction there. That is a no-go. So that's not right, but you can do the reciprocal of the entire quantity and end up here. What about f of 3 to the negative first? Well, I mean, that just means this same thing over here. So we are, of course, going to do 1 divided by 3 times 3 minus 7. 9 minus 7 is 2. How about the inverse? Ooh, that's a little bit trickier. I think people tend to be more comfortable writing the inverse just in terms of x and y, so that's what I'm going to do here. To find any inverse, we switch x and y. However, I can already tell you the inverse here because I know what's happening to x. X is being multiplied by 3 and subtracted by 7. So I know the inverse will do the opposite. It will undo it in the order that things happen to x. And when things happen to x, we just follow PEMDAS, right? So I think this is being multiplied by 3 first and then subtracted by 7. So my guess is the inverse will subtract 7 and then divide by, or add 7 and then divide by 3. But let's double check. The algebraic way to do this, we switch x and y. So x equals 3y minus 7, and then we re-isolate y. So we add 7 to both sides, and then we divide by 3. X plus 7 quantity divided by 3. Or if you wanted, instead of dividing by 3, it might be easier to think of it as 1/3 times x plus 7 equals y. Right? And it seems like I was right. The first thing that happens is you add 7, that's in parentheses, and then at the end, you divide by 3. Now, if we wanted the inverse of 3, I can think of a couple ways to do this. However, probably the easiest way is to just take my formula and substitute in 3. So 1/3 times 3 plus 7, that's 1/3 of 10, which is, of course, 10/3. All right, f prime of x. Finally, some calculus, some easy stuff. Okay, f prime of x, well, the derivative of a line is just its slope. So f prime of x will equal 3. Nice. F prime of 3, well, if the slope is a constant, then no matter what value you evaluate in our derivative, the answer will be that constant. Moving on through. What about the derivative of the inverse? where's the inverse? My inverse equation, oh, that's this guy up here, or if you want this guy over here. So our original equation is 1/3 times x plus 7, but to take the derivative, you might be more comfortable distributing that 1/3 x plus 7/3. Because then, when we take the derivative, and maybe I should be using that inverse notation for all this up here to show what this actually is, but when we take the derivative of the inverse, then this is just a linear equation, and the derivative will be 1/3. And notice it's actually just the reciprocal of the original slope, too. And it turns out that that really is the relationship. It is the reciprocal of the original function's derivative. But things get a little bit trickier. However, if we wanted to find the inverse's derivative evaluated at 3, lots of stuff going on here, right? We just take my constant and we get 1/3. Nothing too bad. All right, let's go ahead, please, and try one more. The function's a little more complicated, nothing bad, x cubed plus x minus 1. Please find these 3 things and then unpause once you're ready. All right, well, the first one might have been a little bit tricky. We switch x and y, so we have x equals, and we do have to replace both of these with y. Then we go, okay, let's isolate y. X plus 1 equals y cubed plus y. Uh-oh. I don't know how to bring those y's together. I think we might be getting a little bit stuck here, so maybe let's get some help. So I'm not quite sure how to find the inverse of this function. Honestly, algebraically, I don't know. So I'm going to turn to some technology. I originally put this calculator in. I'm going to have to take this out because it wouldn't actually find the inverse for me. It said, no, I refuse to, and it was very grouchy. So instead, I'm using my old friend Wolfram Alpha. So I have it, I think, already pulled up for us. And we're going to ask Wolfram to find the inverse of this function, x cubed plus x minus 1. I hit submit, and hopefully it doesn't let me down. Oh, it didn't. Wonderful. Look at that beautiful inverse. Well, I've got to tell you, I really do not know how they found this inverse, but they did. And they verify it by showing you the graph, right? If I scroll down a little bit, you can see our 2 graphs separated by that line y equals x. You can see the symmetry. You can see our x cubed graph looks like this, right? It's over here. And then my, I don't even know what graph, some weird cube root graph is over here in blue. So, if you are asked to find the inverse of this, I think you might be in a little bit of trouble. However, can we still figure out these other 2 values? Let's see what we can do. So this one says, please find the 9 when evaluated into the inverse function. Well, if we can't find the inverse function, how do we figure out what the output is for 9? Well, here's what I always do. I make 2 quick little charts, and I say, okay, we're going to look at one function, x comma f of x, and then we're going to look at the inverse, x comma inverse of x. And that was supposed to say inverse, but apparently I don't know how to write a -1. Rough life. There we go. And what are we trying to do? Well, we are trying to input 9 in the inverse. So I'm trying to input 9 and figure out the output. Well, why did I write the other table? That's because of the relationship with inverses and the original function. The relationship is I can just switch these guys, and I can say the output is 9. What's the input? How does that help? Well, I know the original function, so I could just set 9 equal to the original function and see if I can figure out x. Now, this is still very challenging to solve. It's challenging to solve for the same reason that it was challenging to isolate y. In fact, I don't think you have the algebraic tools to do it. You can always impress me and try to do it, but I think it's not going to work out. Instead, just use what sometimes we call inspection to figure out the answer. Let's just try some small numbers. If I try 0 for x, the answer is -1. That's not it. If I try 1 for x, 1 plus 1 is 2. 2 minus 1 is 1. That's not 9. If I try 2 for x, that's 8 plus 2 is 10 minus 1. That's 9. So this becomes true when x is 2. And if I gave you a problem like this, it would be a really easy one, like this, 0, 1, 2, maybe -1, something like that. Nothing too crazy. So that tells me then that when I input 2 into the original function, the output's 9. How does that help? Well, then we know that the opposite relationship is true. When I substitute 9 into the inverse, then the output is going to be 2. So this is 2. Now, very cool, but then we get to the real struggle. And the real struggle is, how do we find the derivative of the inverse at 9? Because that, to me, is one too many steps. We could use the original function to find this, but unfortunately, the relationship for the derivative of the inverse is not that easy. I cannot just take the derivative, 3x squared plus 1, switch x and y, and then substitute it in there. Once we get to slopes, it's not as easy as just switching x and y. So we need something else. What is that something else? Well, it's the formula for the derivative of any inverse, the title of this lesson. What it's going to open up for us is, without having the inverse function, just relying on the original function and its derivative, we will be able to find the derivative of the inverse. So let's begin. As always, when we're looking for a derivative, we want to try and phrase this using functions that we know how to take the derivative of. And in this case, what we're going to do is we're going to take two functions that are in fact inverses. So I'm going to plug an inverse into its original function. And we know from the opener, when you substitute an inverse into its original version, the answer is x, right? The original strips away everything the inverse is doing to it, leaves it with x. We can take the derivative of that. So we're going to go ahead and take the derivative of the left side. And of course, we're going to take the derivative of the right side. Try that on your own. And what do we get? Well, we end up, of course, the derivative of x is 1. Nothing bad here. How do we do the derivative of this guy? Well, I'll do it in green. We have an outside function, so we need to do the derivative of that first, and of course leave the inside the same. But then, because we left the inside the same, we need to multiply by the derivative of the inverse. And this notation for the derivative of the inverse is pretty weird. It's a strange hybrid function notation. So it says, here's the derivative. We want to take the derivative of that and have a function that's in terms of x. And that's all one term. It's not the derivative of the inverse times x. No, it's all of this of x, just like f of x, a very complicated f of x. Of course, our goal at the end of this is actually to isolate this. We want a formula for the derivative of the inverse. So how do we do that? Well, we take, of course, the one that's on the right side and divide it by everything we don't care about on the left side, and that is the derivative of the inverse of x. And actually, we're done there. This is the last formula that we need to know. Now, I'm going to do, I'm going to take this down one further, and I'm going to say that we either need to memorize this guy or the one below. I'd say probably the first one, though. The first one is just of x. The one that I boxed second, the one down here, is just using the formula with an actual value, because when we use it, we're always going to have a value plugged in there. Well, I would honestly say that probably you shouldn't memorize this. I would really say just start with this every time and take one derivative, and then you don't need to memorize it. However, then you're memorizing this up here, which you should already know. So there's some memorization involved either way. If you can memorize this, 1 divided by the derivative of the inverse of x, then you're fine. That's the last derivative formula you need to learn, I promise. I'm not even lying this time. It's exciting. Well, how do we actually use this? Well, a lot of students struggle because what the problem is going to say is, here is what we want you to do. We want you to find the derivative of the inverse at this value a. And you're like, cool, I know how to do that. That means I work with this formula over here. And you're right. But in order to evaluate this formula, you do need to be good with an order of operations. We need to start with the inside first. So we need to determine the value of the inverse at a. How do we do that? Well, most of them are going to look like what we did up above. You will not be able to find the inverse. So either they are going to give you the value, right? Think of this as f inverse of a. We found f inverse of a. We found that that was 2, and they're either going to tell you it's 2, or it's going to be a very easy problem to set up so that you can see it's 2. So that's our first step. Okay. This then gives us, and I'll try to highlight this, we have now found this value. So what do we do now? Well, now we've found a value for it, and so now all we need to do is find f prime of that value. Well, how can we find f prime? Well, notice it's not the inverse of f prime. This is just regular old f prime. This means take the derivative of the original function that we actually have and plug in our new value. And then once we've done that, we're really done. It's just 1 divided by that value, or the reciprocal of that value. Okay? So let's see. Now that we need to find f prime of our new value, so to do this we need f prime of x, then find f prime of the value. And we're done. That's it. So let's take a look at a quick example. We're going to find f inverse prime of 9 from the top of this page. Okay, what are we trying to find? We want to find f inverse prime of 9. How do we do it? We have a formula. 1 divided by f prime of the inverse of 9. Okay? I always try to keep both the left and the right side here so I don't lose track of what's happening. So I'm trying to find f inverse prime of 9, and we do that for 1 divided by f prime. And now let's find f inverse of 9. But again, we did that earlier. F inverse of 9 is up here. The output is 2. So this becomes 1 divided by f prime of 2. F prime of 2. How do we figure out f prime of 2? Well, we're going to go one more step. We're still looking for the derivative of the inverse at 9, and now we know it's 1 divided by f prime of 2. But we found up above that f prime of x, and I'll show you guys again, f prime of x, it's even circled up here, is 3x squared plus 1. And so we can, if we're looking for f prime of 2, evaluate f prime of 2. Let's see, f prime of 2. Awesome. And we'll just do this little run-on math sentence here. And it looks like 12 plus 1 is 13. And so we get 1/13. F inverse prime of 9 is 1/13. And notice there's only 2 steps to this. It's really not terrible. We start with the formula. We find one evaluation. We find a second evaluation. The end. Okay, so I have 4 practice problems here for you. They're all a little bit different from each other. On none of these practice problems do you actually have to find the inverse function. In fact, I think on all of these practice problems, it is not algebraically possible, at least in our capacity, to find the inverse function. So please go ahead. You're going to be looking for the derivative every time. If you get stuck on any of them, you can watch my video, or even better, skip it and come back to it. Once you've tried all 4, you can definitely check out my solutions. All right, you're back, so let's go through my solutions here. Let's rock and roll. I will probably try to do all the actual math on the left side of this box. The right side of the box is going to be just some extra calculations that I might need. But let's do the relevant math on the left. What are we trying to find? Let's see, if f of x equals this and h is the inverse of f, then find h prime of 2. Well, first off, I hate when they do this, and I kind of admire it because they're not using the inverse function notation that I don't like, but I think it makes it more apparent what's happening when we replace this. So they told us that h is the inverse of x. So that really means that h of x, if it's the inverse of f, is the same thing. Oh my gosh, I'm really struggling. Is the inverse of f. So that's what they're telling us. So when they're trying to find h prime of 2, what they really mean, if this is h prime, right, h is the inverse, they're trying to find the derivative of the inverse at 2. And we have a formula for that. Our formula doesn't change. It's 1 over f prime of the inverse at 2. Okay, so if I'm looking for the inverse's derivative at 2, again, I always keep it lined up this way. I think it's going to help you keep everything in order. It's going to be 1 divided by f prime of something. What is the something? Well, the something is the inverse at 2. How do we find that? Well, I showed you a trick earlier. And the trick earlier is if I'm looking to input 2 into the inverse and we're looking for an answer, then why don't we look back to the original equation? Right? And my original equation, again, f of x equals x cubed plus x, and say, well, what does that mean on the original? It means we're getting an output of 2 and we're looking for the input. And that's pretty relevant because we actually have that equation. Well, looking at this then, we need to set 2 equal to my equation and then think, what value for x will make this equal to? And hopefully you're yelling at the screen, it's 1, it's 1, it's 1. You're right, it is 1. And so that means that when we input 2 into the inverse, the output is 1. Easy enough. One step to go. The last step is we need to find the derivative of 1. So let's do that. To find the derivative at 1, we first need to find f prime of x. Luckily, we have f of x, and so this becomes 3x squared plus 1. And then we need to find the derivative at 1. 3 by 1 squared plus 1. 3 plus 1 is 4. And there we go. The derivative of the inverse of f evaluated at x equals 2 is 1/4. 1 down, 3 to go. Very, very similar problem. Suppose f of x equals x cubed plus 2x plus 2, and that's the inverse function. Find the slope of the graph of the inverse at the point 2, 0. All right, this definitely seems like another slope, which means a derivative. So let's set this up the same way. We are being asked to find the derivative of the inverse at something. And I'm going to get back to that something, but I'm in the flow of writing the formula, so I might as well do this and fill them in after. Well, sometimes this trips people up, and they're like, wait, it says at the point 2 comma 0. Is that the point on the inverse function, or is that the point on the original function? Because if it's on the original function, then don't I want to use 0? And if it's on the inverse, don't I want to use 2? How do I know? Well, you know because you have the original function. Plug 2 in here. Is 2 cubed plus 2 times 2 plus 2 equal to 0? I don't think so. However, if you take the output and plug it into the input, do you get 2? You do. That means that this point is actually the point 2 comma f inverse of 2. Or if you wanted, it means that f inverse of 2 is 0. It's on the graph of f inverse. So when they say find the slope of the graph, they really mean find the slope of the graph at 2. All right, well, as we clean this up a little bit then, life becomes pretty easy here because they gave it to us. If we wanted to find the inverse of 2, the inverse or 2 evaluated in the inverse is 0. Cool. And then we just have, I think, one more step if we're looking for the derivative of the inverse. We want to find f prime of 0. So we should probably jump back to f of x over here. F of x equals x cubed plus 2x plus 2. And we need f prime of x, nothing bad. 3x squared plus 2. And then we need, of course, f prime of 0. 3 by 0 plus 2, which I think makes f prime of 0 just equal to 2. And we're done. F inverse prime of 2 is 1/2. 2 to go. Let h of x equals x times g of x, where g of x equals f inverse. Oh my gosh, we have 3 different function names here. Use the table of values below to find h prime of 5. Oh, all right, similar idea. Need a little bit more space having done this problem before. Let's start with this gross h of x stuff here. Well, we want eventually to find h prime of 5. That makes sense to me. So let's just start with h of x. We also know, well, no, we can do this first. So h of x equals x times g of x. And because ultimately we want h prime of 5, we know we need h prime of x first. We need the derivative function before we can plug 5 into the derivative. This to me looks like multiplication, so I'm pretty sure we're going to use the product rule here. Right? Something like this, and then something like this, and that with a nice little plus in between. Derivative of x is 1. Keep it the same over here. Keep g of x the same. And how do we notate the derivative of g? That's just g prime of x. Now some of you might say, what about the chain rule? Do we need the chain rule? Sure. But the derivative of x is just 1. And so we don't really need the chain rule here. So derivative of g of x is just g prime. All right, and then I think we need to go ahead and find h prime of 3. Nope, h prime of 5. There we go, and we're doing that because that's what they told us to do. So this to me looks like we're going to find, we should color code this for later on. We need to find g of 5 plus, we're replacing x with 5 times, and I'll do this in a different color, g prime of 5. And that's all fine and dandy, except how do we find g of 5 and g prime of 5? There's no g up here. Jeez Louise, pun intended. Well, g of 5, what else do we know about g? Oh, g is the same thing as the inverse. So if I'm actually looking for g of 5, then doesn't that mean we're actually looking for the inverse of 5? And so if we're looking for the inverse of 5, we're inputting 5 into the inverse here, and we're looking for its output. We want to know what is f inverse of 5. Of course, that really means then that we are thinking about the original equation. We're looking for an output of 5, and what is the input? Well, here's the output. The output of 5 is an input of 3, which means on the inverse, an input of 5 gives us an output of 3. So this is, of course, 3. Nice, and then we're a little bit closer here. So h prime of 5 equals g of 5, which became 3, plus 5 times something. What about g prime of 5? Well, g prime of 5, I think this is going to be very similar to before. G prime of 5, we know g is the same thing as f inverse, but it's the prime of that. So we need to find f inverse prime of 5. We have a formula for that. It's very exciting. It's 1 divided by f prime of the inverse of 5. And luckily, we've actually done a lot of the legwork already. We already know that f inverse of 5 is 3. That's what we found up here, so that's cool. And then to find f prime of 3, so again, this is all to find the derivative of the inverse of f. Okay, f prime of 3, well, let's just go to our table. F prime of 3 is 2. We're not going backwards here, it's just plain old f prime. And so this becomes 1/2. From here, I think it's just a little bit of cleanup, right? We have something like, let's see, h prime of 5, and then we get 3 plus 5 halves, or 5 halves is just 2.5. So I think that's 5.5. And which of these fractions is 5.5? I think that's 11 halves. 11 divided by 2 is 5.5, right? Yeah, that looks pretty darn good. All right, last one. Functions f and g are differentiable. G is strictly increasing. Table below will give some values. We've actually seen this problem several times this semester. Bonus points if you can remember where or what other problems are on it. Hopefully it's your friend by now, but we haven't seen this part of it yet. So if g is the inverse function of g, write an equation for the line tangent to the graph of g at x equals 2. This just seems like a tangent line problem. We got this, guys. So again, I'll do my same setup with a little bit of space for work. We know that t of x is going to be, and I'll again try to color code, the derivative of the inverse at 2, because we're writing it tangent to the graph of the original function, times x minus 2 plus the inverse at 2. Right? We're all about the inverse. I'm not using g here. They want the tangent line to the graph of g inverse. Okay, well, let's get started. Let's start with just the inverse, way easier than having to do the derivative. The inverse of 2, again, just make your nice little chart. It will help you, I promise, even if it seems obnoxious at the beginning. Let's do g inverse here. Let's do g over here. We are inputting 2 into the inverse. We're looking for the output, which means we want it, if we can find the output. Nope, sorry. We know the output is 2, and we're looking for the input. So let's go to our chart. Where is the output 2? Oh, it's right here, which means the input that created 2 is 1. And so going the other way around, g inverse of 2 is 1, and we are one step closer to getting our tangent line finished. We know it's x minus 2, and of course, plus 1. Nice. Last but not least, we need to find the derivative of the inverse of g. So the derivative of the inverse of g at 2, we have a formula for this. Careful with your formula, though. We do not want to write f prime of the inverse of 2, because this is not dealing with f. This is the graph of g inverse. So it needs to be g prime of g inverse of 2. But you'll find that tabular or table problems really cut down on the work because they give you all the necessary values. And in particular for this one, we already found g inverse of 2. That's up here. It's just 1. So I think to conclude my slope of the inverse at 2, we need to find g prime of 1. So looking back at the table, here is g prime of 1, which is 5. And so we have our finished tangent line, 1/5 x minus 2 plus 1. That's as hard as really any of these inverse lessons get. You again do need to add one more formula to your note cards or to Quizlet or whatever sounds good to you, and it is this friendly formula over here. Thank you for your hard work. Don't forget your independent practice, and that's all for today.